So if on the screen you can see bits of food on me, I apologize. Anyway, I'm just going to give a little talk on what's happening in the region and the development of batteries and the unintended consequence the battery technology actually has on the charging infrastructure and how it all fits together. I recently made this little slide up, which is the EV community in terms of batteries and what we're making. And I just started populating this within a little box of 45 miles long. And I suddenly realized I didn't have first tier on, second tier on, material suppliers. And there's a tremendous amount of research, cell manufacture, battery packs, all going on at the same time. I only put my university, Newcastle College, on, but they're not the only ones in it. There's Durham's working in it, Northumbria's working in it. There's others. It's rather exciting. And I know Rachel's on this call and Ryan's on. So I'll put this little one up. This is what I call the horse and carriage, how we can't separate power electronics, machines and drives from the battery, because the machine that does the charging is full of power electronics. It has to go through power electronics to get the battery, and when it comes out the battery, it has to drive machines. We can't have one without the other, and fortunately in the region, we've got a lot of both. However, the electric vehicles evolved, and I'm now going to put the classic EV up on the board. This was the G-Whiz, and it was voted one of the 10 worst cars ever made. And they're still running around in London. There was about 2,000 came into the UK and ended up in London. We've now got these. This is the Lotus, and apparently if you switch everything on and hit it on full power, the battery will last for 7 minutes. 2,000 brake horsepower. So we've got the extreme. So what we've got now is a demonstration of the evolution of the vehicle. And most of this is hinged around the lithium-ion battery. The UK government and Europe and lots of people have said that we have to go through a transition process. And I'm sorry, I keep relating this a little bit to COVID. Unfortunately, the vaccine has to get to about 50 million adults. We've got to convert 39 million cars. It's not that much different, and the vaccine's got to be done as quickly as possible. This effectively has to be in place in the next 9 years. So in our industry, that's pretty damn quick. The transition process we're going through starts with policy, which is essentially what and when. The government keeps changing that on a daily basis just to keep us on our toes. And the next thing is the supply, hence the picture that I put at the start. The technology we've got to 2030 is either hydrogen, battery, or other. The other is what Scotty had on the start on the Enterprise, where there is something that we don't know about, but it will drive vehicles better than batteries and hydrogen. The application is strictly either personal, that's us in our cars, people movement, buses, coaches, trains, or goods movement. That's what we've got to address. And to do that, we need some infrastructure, which gets down to how much do we need, where and when do we need it, what type do we need, and who should put it in. There are magnificent numbers quoted, and the bottom line is everybody says we need more. When I respond to the more with how much, where, when, type, and who, nobody ever responds. But this transition process heads into what most of us are interested in, which is the technology. The technology influences the application. The technology also governs the supply. It also feeds back to the policy, and it determines the infrastructure. And the application leads towards the technology. So it's argument at the moment that for heavy goods, we potentially don't have the technology. We may have the technology in the powertrain, but perhaps the method of storing and delivering the power is not that clear. If we go to the infrastructure, Instead of us all having to go to the petrol station and plug in, we got rapid chargers, which are DC, and we got fast chargers, which are AC. And we can choose where we want to do it. We can do it in transit. We can go to a filling station. We can do it at work. We can do it at home. Or we can do it at the destination, as we've just been saying earlier, when we go to buy wine or try to wear it off at the gym. Power delivery goes from 7 kilowatts to as much as you want. Currently, the kit goes up to 350. Now we get into a series of variables. We have power acceptance curves. We have price of electricity. Then we get down to what you do. What is your state of a charge at arrival? What is the ratio of rapid charging to fast charging? What is the state of charge at departure? That's the same as petrol now. You decide when to put the petrol in and you decide when you put enough in. But the state of health is another factor, because the state of health of your petrol tank doesn't really change. And then we got this thing called randomness. AC charging is different. It's basically a linear feed into the vehicle. Their customer actually has control over some of these factors, and some they don't, like the power acceptance curve and the state of health. But what do the drivers want from public charging infrastructure? Simply convenience, reliability, availability, and at the right cost. So now we're going to investigate a little bit of, well, what do they want? Where do they want it? And how many do they want? We need to store electricity on board, or we need to make it on board. So some vehicles, hybrids, can make electricity on board. Some are series and some are battery only. But what is defined is we've either got to do it at home, at close to, at workplace, in a public place, or in transit. That's basically it. That's the options we've got. But the variables in play are fascinating. So the driver determines the change of state of charge at the start. The power acceptance curve is determined by the manufacturer. The state of health is determined by the chemistry in the battery. The capacity is determined by the manufacturer. The ambient temperature when you fill it varies between July and January. In some countries, that is a huge difference. So in places in Canada, that could be -30 to +20. We also don't know the number of events, how often people are going to fill. We certainly don't know on an annual basis the correct vehicle volume, what the ratio of DC to AC will be, and it's up to the person what the state of charge at the end is. The length of event is determined by the operator, the customer, and when they do it is determined by the customer. So we have a split now. So we have the question of how many chargers do we need and what actually will be the impact on the grid. We've now gone through all sorts of combinations. So you've got your domestic charger. We've got one there which pops out the ground from the curb to charge. I'm not quite sure how that one works when most people put two wheels on the curb. You've got the street side ones. You've got mobile ones, high power ones, lamppost, and now we've got the hubs like the Grid Serve one down in Braintree. I've seen today that Ecotricity are just about to revamp their first motorway services at Rugby, and they have 12 high power chargers. So we started with single high power chargers, then we did hubs, and then we did drive-throughs like the Sunderland one there. And then we start to get these, which is the mega hubs. And this one is opening, it's functioning. It can offer space for 24 vehicles simultaneously, up to 350 kilowatts. It's got 5 megawatts of supply. And this company are working with Ecotricity, and they want 100 hubs opened in the UK. This is the first one. I know they have planning permission for one in Gateshead. The confusion that we had from the car makers was we could have had one plug, but that was too easy. So we went for, the first one was the Fast DC CHAdeMO, which was the Japanese standard. Then Fast DC CCS, which was effectively the German standard. And then Renault decided it would have its own, which was 43 kilowatt AC, which it's now abandoned. But this is why a lot of the pumps filling rapid chargers you come to look like a conventional petrol pump with options. The next challenge we got is, where do people charge? And the current logic is everybody will charge at home. Well, the first chart in 2015, 71% of people charged at home. In 2019, when we did a survey in the region, that had dropped to 44%. 3% at work had gone up to 22%. So what we're finding is the average punter is charging wherever it's free or it's cheap. That's what they tend to do. So they're just behaving in a normal manner. There's a lot of clamour for on-street charging. One of the challenges we have is we have 8 million homes without off-street parking. Do we really want 8 million of those charge points on the street? They will get knocked over, people will fall over them. One alternative is to put lamppost charging in, but that example is not in the UK. Unfortunately, the UK tends to put the lamppost at the other side of the path, which leaves a lovely cable across the path designed for people to trip over. You also have to buy that cable and pay quite a rate. Unfortunately, the lamppost charging is the cheapest, easiest way for a council to hit its charge point targets. Then we come to the postcode lottery. I've given 3 examples there of just rapid chargers, not standard chargers, showing 3 cities, 3 populations, and the number of rapid chargers which they've got in. Now, is Milton Keynes correct or is Cardiff correct? That is the challenge, because what is never published, and I know my colleague Jeff Watson's on this call, on this session, is, are they actually being used? So we know there's lots of places putting lots in, but the published figures are quite difficult to get. So what's the public doing? We've started to look at fast chargers, and we got the rapid chargers, and we got the domestic chargers. So what we're seeing is fast chargers, which is up to 22, but normally 7. People are charging at 8, 9, 10 in the morning. A lot of these are they're driving into cities, they're using car parks where it's free, or they're doing it at work. We've shown an example there, which is Manchester, and you can see the curve is remarkably same to the national picture, and the northeast picture is basically the same. When you move to the rapid chargers, the high power, the curve is completely different. These are people who are out and about during the day charging. And we've also included an example, which is Manchester again. And domestic is the question, when do we all come home? And I'll go back to the, do we all charge at 6 p.m? Now, if there's any questions at the end, Jeff's on this call as well. And what Jeff has noticed is these behaviors are changing as the battery technology changes. So when I started, I had a 24 kilowatt hour Leaf, which had about 86 miles. So people tend to charge and charge and charge. The 24 was replaced by the 30 by the 40, and now there's the 60. So people are now changing their habits. And we did a survey in the region of how often do you charge? And it was only 25% of people said they charged every day. Some said most days, but actually 40% were down to a few times a week. And the other interesting point is that the battery chemistry is changing, but now that we've got the new work from home, I charge my vehicle once a week. That's it, because that's all it does. And what we've also found is, comparing regions, the behavioral habits are different. So we've got different regions charging differently, and we've got those charging habits changing as the battery technology changes. So I've just put those a little bit larger so we can see where the peak times are, where people are actually plugging in. But we're also seeing a variance by month and seasons. but the research is required as to why this is happening. We've also seen situations with reverse logic. The government is convinced that the more chargers we put in, the more cars we will register. And this is one local authority where the number of cars is going up and the actual use of the public infrastructure is going down. So why would that happen? Well, because the battery is getting better, people are not finding that they have to charge when they're out and about. And initially, city centre charging had free parking and free electricity. And what we've seen is once the chargers have come on, the behaviours have changed. This is a chart of Coventry. They've just put in 35 chargers, rapid chargers, and at the moment they've got 2.5% utilisation. But we've put a little box at the bottom of some work that we're doing, and the charger type is rapid. But what we have to find out is, of the population as you are, what percentage of you will revert to what you do now and charge on a rapid charger? What percent will actually charge at home or at work? And what is the charging window? It's 24 hours in the day, but when are people actually going to charge? And there's going to be a big difference between those who are in delivery vans and those who are commuting. So we need to know the average time on the charger. And then we need to know the frequency of charging. So effectively, on this example, you need 4 chargers of every day, 2 chargers every second day, etc. And this frequency is changing as the batteries change. So what you could have now is, if we plan the number of chargers based on the original technology, which we did, we'd have too many chargers. So we've got this lovely thing called the Diffusion of Innovations theory, which tries to find out where the critical mass, the tipping point is, as we've done with vaccine. Norway has got to that point. It's actually passed ICE, internal combustion engine sales. The UK is still around 2.5–3%. So we're still in the innovators, early adopters. If you expand the sort of spreadsheets and things that we're looking at, you need to start projecting, as you see on the cars, 500 cars, 3,000 cars, 4,000, as the number of vehicles grew up. But every time the number of vehicles goes up, new models come on the market with new battery chemistries and new range. So the percent on the Rapid, we've guessed at 20%. That could go to 30% or 10%. The charging window can change as more taxi drivers buy them or van drivers buy them. Will the charge time go up or go down? Now, just imagine if we had a technology which would allow us to charge in 5 minutes instead of 42. That means you can effectively do 8 cars in the time of a current one. So you don't need as many charge posts. So this little graph at the side shows how this numbers of chargers can vary based on the chemistry. We've also got options coming around, such as induction charging. At the moment, there's only one BMW fitting this as an option, but it is a possibility. But the question comes with this is, as the battery capacities get even bigger, and we've just done a recent study, and of all the models coming on the market, the average battery size is 50 kilowatt hours, but several, about 20%, are over 70 kilowatt hours. Can we transfer enough power in time? One of the challenges is, with 35 million light vehicles, if they all plug into a 7 kilowatt charger at exactly the same time, we will have a demand of 24.5 gigawatt hours. Bear in mind, the grid is currently running at about 40 gigawatt hours. So we take half the grid. One of the challenges we've got, if they all went onto a 350 kilowatt hour at exactly the time, we will need 12 terawatts and we will bust the grid. Now, these are the figures which the Daily Mail, etc. use to prove that we can't have EVs. But I'll go through some of the reasons why this is a bit of a nonsense, because we don't all charge at 6 o'clock. One of the things we also have to bear in mind of is temperature increase. As the ambient temperature changes outside, I watched my range vary by about 15% between summer and winter. Until the last 2 weeks, when my car's full, it's 100 miles, it's now 111. So the temperature increase affects how the lithium ions go backwards and forwards, to slow them up or to speed them down. And it can also cause problems. This also has an impact on the infrastructure. If we continually rapid charge at a high rate, it will shorten the battery lifespan. It damages the anode and it does some battery degradation. There's now onboard computers to monitor and measure this. Because the battery chemistry changes so often, we don't have enough research papers on a stable situation to know this impact. I refer to the charging curve, and this is a typical charging curve. When I say typical, it was my old 24, 30 kilowatt hour Leaf. I plotted how the vehicle charged every minute against its state of charge. The different coloured lines are simply I did it at different ambient temperatures, at different state of charge start and end. This is where the famous 30 minutes to 80–85% came from. That was the sort of figure. The tail off is a problem for infrastructure because for the last 10%, it takes 25 minutes. That is not a revenue earner for the operator. They don't want you on. And one operator at one point set a 30-minute limit. That was it. If you have a look, you can see how the power drops off. The blue is the 30 kilowatt, the red is the 24. But I want to show you how this is advanced, but I also want to show you the complications. These were some of the earlier models. So you can see the power curve was different for each model that was produced. So that is a challenge for how much power we're going to take from each charger. We've now got vehicles like the e-tron, the Mercedes-Benz, the I-Pace, that are now taking power in around 150 kilowatts, up to 70% state of charge before the power comes off. Now, this is not a scale, I've just drawn in the characteristics of my Leaf. So you can see the different power drawn between the two. My Leaf will not take any higher than about 50 kilowatts. But now we got much more high power for longer. If I transpose just the original graph onto a time versus state of charge, the state of charge at arrival and exit, I determine that because I decide when to charge and when not to charge. I've shown a theoretical degradation of 20% because that's what my car is, the warranty says. Bear in mind, the top curve is unique for every model, and the state of health impact, it will be unique because it'll be somewhere between 100% and 80%. That profile is the time on the charger. This determines the rate of power delivery, so we're operating in that little space. So this all interlinks between the two. And these are the variables which matter for trying to work out how much infrastructure we need. In the extreme, again, using the Nissan and using a graph that we measured of the first battery chemistry when it got really old, that if you use the original Japanese specification Leaf, taking another 10 minutes to reach 80%, if 30 million vehicles all charged in, we would need another 5 million hours of charging capability. So as I said before, these charts and this calculation is all based on what the chemistry is influencing the driver to do. So let's move to the current energy picture and what role does the battery have in this. This is a little picture of thermal and green power generation into the grid, into a house. That's mine because I knew nobody would sue me for it. And you can have solar panels on the roof. The car is detached from this picture. Technically, we have a feed-in tariff, but the car doesn't contribute. The future relationship is a bit more complex. So what we can have is the grid will do dynamic charging, static charging. It goes to the grid, it goes to the house. You can have PV into the house. You can have power going to your own domestic dynamic charging, static charging, etc. But we're now moving to this. The battery itself has been used in stadiums. In our old life when we worked at kids at college, we had some in the building there. The battery can store energy from solar power from the house, and then it can feed it back into the house. The car can feed power back into the house. So what we can actually do in this picture is we can take the house off the grid instead of just feeding back to the grid. If we have 20 million homes with 5 kilowatt of battery storage, that's actually 100 gigawatts available. Just a thought provoker, that Hinkley Point is 2.3 gigawatts. And there's no reason why I can't sell electricity to my neighbour. So if I'm really cute, I drive to work in the Leaf, I come home with it full because work let me charge up, and I sell it to my neighbour at a dead cheap price, and he's very happy. We often get asked the question, what will happen to the grid if we all charge at 6 p.m? Probably the same if we all went to a petrol station at 6 p.m. Because that would spread 30 million cars between 8,500 petrol stations, which is 3,500 cars per station. And I use this illustration to show what it would look like. Note that's only 1,000 vehicles. So why does this not happen? Because nobody goes at 6 o'clock. However, if you were to put on social media now, there will be a fuel strike from midnight tonight. This is what happens, and we've seen it happen. So what if we reverse the 6 p.m. logic? So the 6 p.m. logic is the grid puts a lot of power into the house, which I put into my car. 20 million cars on the grid because 20 million cars have got off-street parking. What if we did the opposite and took 20 million homes off the grid? That is a possibility. And one of the things that we have to really consider now is what is the algorithms and the cost benefit of doing this sort of thing? What does the regulator cope with this? What is the value by the participant? Will the battery chemistry allow us to do this? Will it be happy for us to do this? And then we got the challenge of end of life. Warwick Manufacturing say that in 2040, there will be about 1.4 million EV battery packs per year, which is about 203,000 tons of batteries. For those of you not familiar with the battery, I thought I'd circle it and show what the size is. I thought I'd also put the dimensions on and put it into simplistic terms. They will fill St. James's Park to the highest point 1.5 times. There is no industrial capacity in this country for lithium-ion battery recycling. At the moment, the values are quoted at about 1,200. At the moment, it costs £1,000 to get rid of a battery. But the battery chemistry determines the material supply. The battery chemistry determines the recycle value. There's a lot of talk about taking cobalt out of batteries. But if they do that, the recycle value starts to go down. It takes about 5 to 8 years to open a mine to produce the copper and cobalt or nickel and cobalt that's required. Nobody is going to open the mines and a cost of a few billion to produce the product that the battery chemists are going to design out of the batteries. Nobody is going to open recycling plants for the 1.4 million batteries if there's nothing in there of value to take out. These questions are all being challenged and looked at by the Faraday Institution, a brilliant group of people, part of the industrial strategy, who are looking at all of these questions. What is the new chemistries of the future? Can they come up with solid-state batteries, which will give us 5-minute charging and 500 kilometers distance in one charge? If we do, that's absolutely wonderful. Are the batteries that we produce today suitable enough and up to speed for HGVs? Will a holiday coach leave Newcastle and get to Rome in a simplistic manner without having to stop every so often for an hour? There's lots of questions not answered yet. And this is what I think, for one, we as a region, with the people, the technology, and the research that we've got, should be really challenging it. Thank you. I hope you found that interesting. Any questions?
Thank you, Colin. I've just posted in the chat function that if there are any questions for Colin, please ask through there. One question from, well, a couple of questions from me actually, Colin. I guess the 6 p.m. charge is based on human, just usual run of the business, return from